All right, welcome back again, everybody. Today we're going to be doing section 11.4, which is where we get a bunch of my favorite theorems, the comparison tests. We're going to get the direct comparison test, and we're going to get three different limit comparison tests. So just keeping with the theme of developing all these theorems and all these tests that we can use them to test the convergence or divergence of series. So let's move along. All right, so here's the overview: direct comparison test, the limit comparison tests, and then some important notes. This actually is a much shorter section, so the section is not too long, and this shouldn't be too long of a lecture, but the content here is also very critical. The techniques that we use here are like fundamental techniques for looking at series. In particular, the direct comparison test is fundamental. We're going to use it a lot. You're going to use it a lot. So you do want to make sense of it all. And this is also where things start to get a little more creative and a little more organic, which is kind of fun. All right, so let's start with, let's start with this. So just like we developed a comparison test for improper integrals, you might remember from, I forget which section it was. I can't remember what section it was. But we developed a comparison test for integrals, and the way that we did it was we compared the size of the integrands, right? The functions that we are integrating. Just like that, we can develop a comparison test for series by comparing the size of the summands. The summand is the sequence that you're adding up. Those are the summands. In practice, this is why we had this result from last time. In practice, comparing your summand to that of a p-series or that of a geometric series can be really, really helpful. And the reason for that is we know about the convergence or divergence of p-series, and we know about the convergence or divergence of geometric series. So the general idea is you want to compare with something that you already know about. You don't want to compare to something that you don't know about yet, at least. Or if you're forced to compare to something that you don't know about, you want that thing that you don't know about to at least be approachable, and maybe you can figure information out about it. All right. I think I do this in another lecture, like in a later section. Let's see. Oh, it's also helpful when bounded functions are present in your summand. So for example, our favorite functions, sine, cosine, arctangent. We love those functions because they're bounded. So when you see those functions, direct comparison can help a lot because you know how big those functions are. Here's a pro tip, and I'll say this when we're working in activities together, and I'll say it more. You want to stop using the word it. You want to stop using the word it. More specifically, stop saying it converges or it diverges. You have to be specific. So you'll hear me say this a lot. I'll be like, "What do you mean by it?" And then I'll say what converges, what diverges, and so on, because we're going to use the convergence or divergence of one series to talk about the convergence or divergence of another series. So you can't just say it converges. You have to be very specific with what you're saying converges. So that's my pro tip. Stop using the word it. All right, so here's the direct comparison test. Suppose that you've got two series with positive terms. If this series B sub n is convergent and the A sub n terms are always less than the B sub n terms, then the series of A sub n is also convergent. Similarly, if the series B sub n is divergent and the terms of the series with B sub n in it are always smaller than the terms of the series with A sub n in it, then the series A sub n is divergent. So I'm going to throw the thinker up again. Ponder that for just a minute. Reread that in your head for a minute to make sense of it. Right? And then now say it out loud to yourself a few times. So just speak it out loud to give your brain that feedback. Okay, and then I'm going to talk about it a little bit more before we start using it. We're going to jump into some examples very quickly here. This is basically saying if you've got a series that's convergent and you're investigating another series and you notice that all the terms of the series you're interested in are smaller than the series of this other one that you know is convergent, then yours has to be convergent. Your series has to be convergent. That's really what it's saying. So it's that same like dominating behavior. If you know this series is convergent and the terms of your other series are always below, then this one was always also going to have to converge. So there's a domination relationship there, and vice versa. If you've got a divergent series and you know that the terms of your series that you're interested in are always bigger, then your series has to diverge also. That's really what it is. So again, you are comparing the summands to get information about the series. Okay, that's a critical thing to make sense of. We are not comparing the series outright. We are comparing the terms of the series. And when we compare the terms of the series and we have a result about one of the series, we can get a result about the other series. Okay, so there's a subtlety there. All right, let's see how it works. We're going to determine if this series converges or diverges. And one thing I want to say right off the bat is we are not asking what it sums up to, right? We're not asking what it is equal to. We're just saying, does it even converge or does it diverge? I have no idea. So what I want to do first here is I want to throw up the thinker for a minute, and I want you to just ask yourself, what do you think? Do you think it converges or do you think it diverges? All right, now make a claim. Do you think it diverges or converges? Say it out loud, and then we'll go from there. All right. For me, I have a feeling that it is going to converge. And the reason that I think it's going to converge is because I see this 1 over 2 to the n, right? And 1 over 2 to the n looks like a geometric series. It looks like a geometric series where the common ratio is 1/2. And I know that converges. And the only difference between those terms and these terms is this +1. And that +1 really shouldn't affect that much because as n gets really big, that's going to be the dominating term. So this is really what's dominating the terms of these series. And this is just a little like bip. It's like a little tack on to each one of those terms. So I suspect I suspect that this series will converge. But just because I suspect it doesn't mean that it's true. I need to prove it. I need to prove that it is true. So we're going to use the direct comparison test. Here we go. So, like I said, this series is very similar to this geometric series. We know this geometric series converges because 1/2 is less than 1. So if I can show that the terms of the series I started with are less than the terms of this geometric series, then the comparison test will tell me that the series I'm interested in will converge too. But that's actually an obvious result. So look at this comparison. 1 over 2 to the n plus 1 is strictly less than 1 over 2 to the n, because this is a bigger denominator. 1 over 2 to the n is equal to this, and these are the terms of that geometric series. So we've shown that the terms of our series are strictly less than the terms of a convergent geometric series. Therefore, by, where I didn't even state it, I should have. Therefore, by the comparison test, our series converges. And that's the proof. That's the proof. That is the result. Um, yeah, that's it. That's the result. So this is a lot of what your work is going to look like in this chapter. This is a perfect example of it. So the question will be this: determine if the series converges. What do you have to do? You've got to do some comparisons. You've got to use some inequalities. You've got to see how the terms are related to one another, and then see if you can compare to something that you know about. And then if you know about the convergence of a series, maybe you can leverage that to determine convergence of a different series that you're interested in. And that's what I did here, right? Notice the calculations were actually pretty minimal. The calculations were this. That's the calculation. The what's the word? I can't even think of the word. The bulk of this result, the bulk of this question, the bulk of the work is stringing together those theorems and making a conclusion. That's what you got to do in this section. Okay. All right. Okay, so now let's do a different example, and this is going to lead us into the limit comparison tests. So let's consider this series, right? This series. Now, this is similar to the series that we were just looking at, but it is not the same. And there's actually a pretty big difference in some sense. And the big difference is this negative. The series we were looking at before had a positive here. It was 2n plus 1. Now it's 2n minus 1. And the reason that that's a little bit of a problem is because 2 to the n minus 1, or I'll say this, 1 over 2 to the n minus 1 is bigger than 1 over 2 to the n. It's bigger than 1 over 2 to the n, right? Because this is going to be what is it? A smaller denominator. So you're going to get a bigger number. All right, so you might think that you could do this comparison and say, oh, let's compare it with that geometric series. But that comparison is actually useless because the direction of the inequality is the wrong direction. It's going the wrong direction. These terms are greater than these terms of a series that we know converges. No help. That's no help. The terms of our series are bigger than the terms of a series that converges. No help. That's no help because the inequality is the wrong way, right? Our stuff is bigger than something we know converges. So we don't know anything about what's going on with our stuff, right? So you got to be careful with these. You got to think about the inequalities, you got to think about the implications, all that stuff. So the direct comparison test in this case, or at least with this type of this example, isn't helpful here. The direct comparison test isn't gonna help. However, when we look at the terms of this series, again, it seems like we should be able to compare it to that geometric series, and we kind of get this feeling that it's going to behave similarly to that geometric series because again, this minus one doesn't really affect that much. That's just a tiny little bit in the grand scheme of things. So we suspect it should converge. Like I think it'll converge because it's very much looks like this. But direct comparison doesn't help. This is where the limit comparison tests can be very, very helpful. In my experience, my students love the limit comparison tests because they're nice. Um, but I always prefer direct comparison. It's just such a pure form of proof. I like it. All right, so here is the first limit comparison test. So this is the limit comparison test in the case when C is positive, strictly positive. And here's what it says. Suppose that these two series are series with positive terms. If the limit as n goes to infinity of an over bn is equal to some number c greater than 0, then either both series converge or they both diverge. That's what this is saying. So in other words, look at the limit of the summands, and if the limit of this ratio converges to a positive number, then the series have the same behavior. They either both converge or they both diverge. So this is great. One thing I'll say about this is kind of like with the direct comparison test, you've got to know about one of the series. So in practice, there's a series you're investigating and there's a series that you know about, and you're trying to compare the two. So one of these series has to be a series that you actually know something about in terms of convergence and divergence. Otherwise, the result is not helpful. All right? Another thing I have to emphasize is this number does need to be strictly positive. It can't be 0 necessarily, and it can't be negative, and it can't be infinity. Those are the other cases. Those are the other cases. So you need this to actually result in a positive number. All right? This one we're going to prove. Because the proof is helpful, and the proof is good to think about so you can make sense of how it works. So here we go. We're going to let little m and capital M be positive numbers such that C is sandwiched between those two. We are allowed to do this because C is a strictly positive number. So the Archimedean property tells us that there is a number less than it that is positive, and there's a number bigger than it that is positive. All right? So C can be sandwiched between these two numbers. Now, by the precise definition of a limit, there exists a capital N such that for all little n greater than n, this result is true. This is by the precise definition of a limit, because again, we're assuming that this is true. Yeah, this is the hypothesis, right? So if this is true, then these things must both have the same behavior. That's what it's saying. All right, so because we know this is true, because we know that that limit exists, um, we know that there is a point where this will be true, that m will be less than that ratio and capital M will be bigger than that ratio. Multiply both sides or all sides by b sub n, and you get this. All right. So in essence, the terms a sub n are trapped above these terms and below these terms. Okay. Now, if this series converges, then this series also converges by linearity. That's just linearity of convergent series. And so this series must be convergent as well by the direct comparison test. So the direct comparison test is giving us the result of the limit comparison test. So basically, again, if this converges, then this converges, and because we have this order relationship, the series with a sub n in it must also converge. That's the idea. Similarly, if this series diverges, then so does this series, again by linearity. And because we have this order relationship, that means that the series with the a sub n terms must diverge by the direct comparison test. And that's the result. That's the limit comparison test. So in other words, if this ratio converges to a positive number, then your series have to have the same behavior. Let's try it out. Okay, so this one I want you to try on your own, and then we'll do it together. So let me throw up the thinker for a minute. Determine if this series is convergent or divergent using the limit comparison test. What's a series that you would want to use for comparison? Think about that. Okay, now say something out loud. What's that series that you want to compare to? All right. Now try to work it out on your own. Remember, write complete sentences. Write out your argument with complete sentences. Show the comparison, cite the theorems, all that stuff. Okay, now let's do it together. Uh, Maybe not surprisingly, the series that we want to compare to is that geometric series 1 over 2 to the n. Here we go. So let's let a sub n be the terms that we're working with in our series, and b sub n be these terms, 1 over 2 to the n. And we want to investigate this limit. So we're looking at the limit of this ratio. Doing some basic algebra, we can simplify it to this. Divide by the highest power, and you get this. And then as n goes to infinity, this goes to 0. So the whole thing goes to 1. 1 is bigger than 0. Nice. That means that the series with these terms and the series with these terms have the same convergence behavior. Excuse me. Now we know this one is convergent because it's a geometric series. So by the limit comparison test, this one is convergent as well. And that's the argument. That's the argument. All right. Once again, notice the calculations are pretty limited here, or pretty minimal here, right? What's really going on is us stringing together this chain of logical deductions that allow us to now assert that this series has to be convergent. All right? Okay. All right, so now let's look at the other limit comparison test. It turns out that you can still use this when c is equal to 0, but there's an additional assumption that you need. So let's look at this one, and then we're going to use it again. We're going to use it as well. Suppose that you've got two series, an, bn, and they've got positive terms. Suppose also that the bn series is convergent. Okay, that's the series whose terms are given by b sub n. Then if this limit, the limit of a sub n over b sub n, is equal to 0, then the series with the a sub n terms is also convergent. Okay, also convergent. So again, I'm going to throw up the thinker, read this note that I have at the bottom, think about this theorem, say it out loud in your head a couple times. I'll even say this, and say it out loud, and say it out loud. All right. Okay, so now let's talk about this a little bit, and then we're going to use it in an example. So for one, you still have this relationship. You want to look at this limit, a sub n over b sub n. But the additional assumption we have here is critical. We're assuming that the series of b sub n is a convergent series. And this is saying that with that additional assumption, if this still gets you 0, then the series with a sub n's must also be convergent. Okay, so it's a little bit more particular than the previous limit comparison test. The previous limit comparison test just said, hey, they behave the same way, right? That's all it said, as long as this becomes a positive number. This is saying, hey, if you do get 0, but also the b sub n series is convergent, then a sub n has the same behavior, the series with a sub n as terms. All right? So let's use it. Let's try it out here. Let's determine if this series is convergent or divergent. And what I want you to do in this case, well, try it out. This one might be a little bit tricky, but I want you to think about it for a minute and think about what is a series that you would use for comparison and see if you can set up the ratio and take the limit. All right, so think about it for a minute. All right, now say something out loud about what series you're going to use for comparison. Okay, now try to work it out on your own. See if you can, write out complete sentences. See if you can use the limit comparison test that we just looked at to determine if this converges or diverges. All right, now let's do this one together. This one can be a little bit tricky because it kind of depends on what you choose. That's the thing. When you're trying to do a comparison, you get to choose the series that you're going to compare to. But not every comparison is a meaningful one. So you have to choose a series that will give you a meaningful comparison, and that can be difficult in practice. So here is actually what I'm going to choose. So we're going to let a sub n be these terms. I'm going to let b sub n be 1 over n squared. It's going to be 1 over n squared. Um, if you tried 1 over n cubed, you might have come up against something that didn't work, right? Because if you use 1 over n cubed, I think you end up getting ln of n, and that doesn't go to 0 as n goes to infinity, it goes to infinity. So in that case, that would not be a helpful comparison. So the tricky part here is we're going to compare to this instead. We're going to compare to the series 1 over n squared. What do we know about that series, or the series that has 1 over n squared as terms? What do we know about that series? Well, this series converges by the p-test because p is greater than 1. P is equal to 2 in this case. So we know this converges. Now let's look at this ratio. Plug in what we know, ln of n over n cubed, 1 over n squared, and then when you simplify, you get ln of n over n. Now, we need to investigate that limit, but here's the catch. It's of the form infinity over infinity, right? So when it's infinity over infinity, we feel very tempted to use L'Hopital's rule. But remember, L'Hopital's rule requires differentiability of the numerator and the denominator. So these are not differentiable functions, they're sequences, right? So we have to pass to a real variable extension. We have to consider the related function, ln of x over x, and now we can apply L'Hopital's rule because we have differentiable functions. So here we go. The limit as n goes to infinity of this is equal to the limit as x goes to infinity of this. We apply L'Hopital's rule. Oop, I forgot there's a typo here. And then we get limit as x goes to infinity of 1 over x over 1, which is 0. There we go. Now, because that limit is equal to 0, by the limit comparison test, our series converges, the original series we started with. Hooray! All right. Again, this is how the arguments go in this chapter. You have to string together all these theorems. The calculations are rather minimal. What's really important is all of these things, picking a series to compare it to, talking about the series that you know about, knowing if that series converges or diverges using like the p-test, or it's a geometric series or something like that. Maybe having to pass to a real variable so that you can use differentiability to your advantage. And then you string together all of these tools and you get the conclusion, which in our case is that this converges. All right. Okay, now the next one, if you tried to do 1 over n cubed as your comparison, then you would end up getting infinity, right? You would end up getting infinity, if I remember correctly. So let's talk about the case when that does happen. The limit comparison test, the case where C, maybe I should say quote unquote, equals infinity. And here's the statement. Suppose that you've got series with positive terms again, and suppose that B sub n, the series B sub n, is divergent. Then, if this limit ends up being infinity, then the series with A sub n is also divergent. Okay, so this is another one where I'm going to throw up the speaker, or the thinker and the speaker. Read this out loud in your head and then say it out loud with your voice. Go for it. A few times. All right. Now let's use another example in a minute here. Oh, but before I go to that example, again, this additional assumption is critical. So the order here is still the same, an over bn, but now we're supposing that this series bn is divergent. And if that series is divergent, and this is the case, then the series with an must also be divergent. All right, let's use it. This one I want you to try on your own too. So this one is not as tricky as you might think. But think about it. So let me throw this up. See if you can determine if this is convergent or divergent. And what you should say out loud to yourself is, what is a series that you will compare this one to? Try it out. All right, now work it out. See if you can write out the argument. Write complete sentences, write your calculations, do the comparisons, and then we'll do it together in a moment. All right, here we go. Um, Well, the series, okay. Let me see. 1 over ln of n, adding all those up. Well, I have a hunch that this is going to diverge. I have a hunch this is going to diverge, but I don't really know. That's another thing that's tricky about these types of problems. You don't really know, but I have a hunch that it's going to diverge. And just as a guess, I think I'm going to try to compare it to the series 1 over n, the harmonic series, which I know diverges. So here's how the argument goes. Let a sub n be 1 over ln of n, and b sub n be 1 over n. Now, by the p-test, I know that this series diverges, or just by the proof that we did earlier in this section? No, last section. Yeah, last section. I know it diverges. So now let's look at this limit. Limit of an over bn equals limit of this over this. Simplify, you get n over ln of n. And once again, we have an infinity over infinity situation. So let's do a real variable extension. Let's consider the related function, x over ln of x, and let's apply L'Hopital's rule. So this limit is equal to this limit. Oh, I forgot the limit again. That was a copy-paste error. Limit as x goes to infinity of 1 over x is equal to the limit as x goes to infinity of x, which is infinity. Boom. Since I know the harmonic series diverges, by the limit comparison test, the series that we began with also diverges. And that's how this goes. That's how this goes. So, yes, that's how these things go. All right, so last but not least, some important notes. Now we've seen how to use these different comparison tests. We're going to get a few more tests in the next couple sections. But I want to be very clear about this. The solutions that you see here and in later examples are models of what your work should look like. Emulate them. I want to be very, very clear about that you should be trying to make your work look like the solutions you see on these slides. and the solutions that you see in the book and the solutions that you see in the activity solutions. That is the goal. So write complete sentences, all of that stuff. Oh yeah, there it is. You need to write complete sentences. They need to be coherent sentences that explain your arguments. You're writing proofs. We are literally doing proofs at this point. So be precise and be clear and careful. I've said this a couple of times. You'll notice the calculations are really rather minimal. They might be minimal. And what really is important here is your explanations and your reasoning. So you need to be able to clearly explain your reasoning of why a series converges or diverges. All right. And following immediately from that is this very, very important note, because a lot of times students will say, hey, if I get the answer right, do I get some credit? The answer is not really much credit in this case, because the answer at this point is really just yes or no. Does a series converge or does it diverge? Yes or no? You've got a 50-50 chance of just guessing that it's right. So you could just throw out a random guess. Like when I look at this series here, this one, I guessed that it was divergent. I was like, it feels like it's going to be divergent. That's not a proof. That's not a proof. That's not an assertion. Like you can't claim that that's true because you got a hunch. You have to prove that it's true. So yes or no is not a sufficient answer. You've got to actually prove it, okay? So, last most important point here, justifying why the series converges or diverges is everything. It's the why, not the what. Because again, it's yes or no. What's more important is why. Why does it converge or why does it diverge? All right. And on that note, let's play. So I'm excited to do these sections with you. These sections are some of my favorite sections, but I got to admit they are also pretty tricky. So if you're not used to this kind of argumentation, if you're not used to writing proofs, if you're not used to working with inequalities in this way, it can be a bit of a learning curve. But I'm here to help you, so I'm more than happy to help you learn this stuff. It really just takes some practice. Uh, I'll also emphasize again that you should work in groups. You should talk to each other about these ideas. You should show your work to your group members and be like, does that make sense? And they should also critique your work and so on. So please work in groups. Uh, you're more than welcome to ask as many questions as I've got time to answer. And on that note, I'll say goodbye and I'll see you next time. Take care.